Now that we've discussed orientation, we are in a position to define the surface integral of a vector field over a surface. So if you have a vector field f and an oriented surface, so remember we have to be able to put an orientation on it. The oriented surface S, we've chosen an orientation in, so that's what the unit normal vector is. Then the surface integral of f over that surface is just going to be the scalar surface integral of the dot product of f with that normal vector. So f dot in is going to be a scalar function of the points on the surface, and we're going to integrate that scalar function over that surface the way we did in the first video of this section. In a sense, what this measures is how much the vector field is flowing through the surface in the direction of the orientation. So if we have a surface here and the normal vector is going out this direction, if our vector field comes through like that in this direction, then the dot product of these two vectors is going to be positive. So as long as we're kind of going in the correct way through the surface, then we get positive results. But if down at this point our vector field is going in that direction, now it's kind of going the wrong way. It's going backwards through there, and the dot product of these two vectors is going to be negative. So we end up getting maybe positive parts through some parts of the surface, negative results through other parts, but they correspond to what direction the vector field is moving through the surface. That's why in physics and a lot of other sciences, these kind of integrals are referred to as the flux of the vector field across S. For instance, if F represents the flow of water, and maybe S is the boundary of some cell, a biological cell, then there might be water flowing into parts of the cell at some parts, but flowing out of the cell at other parts. And the surface integral will tell you the total amount of water that flows out of the cell. Now remember that because we do want to have a positive orientation pointing outwards, that means if we get a positive result, that means more water flowed out of the cell, and the cell lost water overall. And if we end up with a negative result, that means more water went into the cell, and so the cell gained water overall. But it's a way of actually kind of adding up all of these results across the entire surface. Well, what is the best way of computing these integrals? Remember, we saw that if our surface is parameterized as r of uv over some region D, then the unit normal vector is given in the form of n equals r sub u cross r sub v over the magnitude of that. That means that our integral, our surface integral of f dot ds, this would be a capital S, is going to be the double integral. Let's say, I guess it will be the surface integral. We'll get to a double integral in a moment. But we'll have f dot our normal vector of ru cross rv over its magnitude. But that is a surface integral in the original sense. So this would be a bold S. This would be a not bold S. And we turn that into a double integral over D of f dot ru cross rv over the magnitude. But with a surface integral, we end up taking this scalar function and we multiply it by the magnitude of ru cross rv. And we integrate that over D. In other words, since we can go ahead and cancel out these two magnitudes, we can calculate the surface integral of a vector field by simply taking the integral over D of f dotted with ru cross rv. Which is actually pretty nice because we don't have to deal with any of the square roots. This is kind of how things happened with our line integrals earlier. Of course, in the special case of a z equals g of xy, we can do kind of the same thing. Remember, we had our parameterization where we set essentially x equals u, y equals v, and then our z component, which is be g of uv, or we can just leave it in terms of x and y if you want to. In that case, Rx cross Ry is just going to be the negative derivative of g with respect to x, I, minus the derivative of g with respect to y, j, plus k. Remember, that was our positive orientation, or our upward orientation that we looked at in the last video. And so when we put it into this kind of formula, and we say that f is pi plus qj plus rk, we get the formula that the surface integral of f over, or dot ds, is the double integral over whatever region d that we form the surface over, of negative p times the derivative of g with respect to x, minus q times the derivative of g with respect to y, plus r. Now you can either remember that formula, or you can remember, well, you definitely want to remember this formula. This is the formula that we definitely want to keep in mind. If you want to derive this formula every time, you can go right ahead. I usually just keep this one in mind, because it's the more important one. But let's jump into some examples of doing this, because being able to work through problems helps a little bit more than just looking at formulas. Let's go ahead and start with problem 22. So here the instructions tell us to evaluate the surface integral, where they've given us a vector field and a surface. And this isn't going to matter for us right now, but it does say for closed surfaces, we're going to use the positive orientation, the outward orientation. But this one is not a closed surface. This one is the helicoid. Remember the helicoid that we looked at both in exercise 7 in the same set of videos, and in the last section, the last set of videos, that's where we actually looked at it before. We looked at finding the surface area of that helicoid. But recall that the parameterization here, we have r of uv is equal to u cosine v, u sine v, and v, where u went from 0 to 1, and v went from 0 to pi. If we go ahead and look at the graph of that, just to remind ourselves of what we're actually working with, we have u cosine v, u sine v, v, u going from 0 to 1, v going from 0 to 2 pi. I think I missed a comma. I missed 2 commas. Thank you, GeoGebra. There we go. Oh. Right. 0 to pi, not 0 to 2 pi. Making little mistakes all over the place. So we're going to integrate the vector field z comma y comma x over this surface. Of course, we did calculations involving the helicoid, both in the last section and in problem 7. So we're just going to recall what we did there. We had the RU cross RV turned out to be sine V I minus cosine V J plus UK. They specifically want us to use the upward orientation, and since our values for u are from 0 to 1, and the k component here is u times k, the z component is u times k, that means we will always be pointing upwards. That's what they wanted. They're basically just saying here with upward orientation that we do want to have a positive z component. And so we have the correct one here. We can go ahead and use this in our integral. Remember that we do have to replace the x, y, and z with our formulas in terms of u and v. So the integral over s of f dot ds is going to be the double integral, where we go from 0 to pi for v, it goes 0 to 1 for u, we have z. Remember, z is v. That's our first component of f, but that's dotted with the first component of ru cross rv, so we're going to put a sine of v here. Then we have y as our second component of f, so u sine v. That's multiplied by the negative cosine v of ru cross rv. Then we have x, which is u cosine v for our third component. And that's going to be multiplied by the third component of ru cross rv, which is u. And then we had du because of the 1 to 0, and then dv for the 0 to pi. All right, now integrating with respect to u first. So here we have just v sine v. There's no u's in it, so we introduce a u. Here we have one copy of u. The rest is in terms of v, but we'll bring out the minus sign, and that u will turn into 1/2 u squared. And finally here we have two u's. So we have a u cubed that will turn into, a u squared that will turn into 1/3 u cubed. To be evaluated from 0 to 1. Of course, when we plug in 0, all the u's will give us zeros. So essentially we just end up plugging in 1. So we have v sine v minus 1/2 sine v cosine v plus 1/3 cosine v. Now we got slightly annoying integrals here. The cosine v is not bad, of course. The sine v, cosine v, we can actually make use of substitution. I would like something like w equals sine v, whereas then the dw becomes a cosine v. So that will turn this thing, when we actually do the integration, we'll be integrating 1/2 of w, and so we get a 1/4 w squared. But of course w was the sine v all along. Unfortunately, the v sine v is the most complicated part. There we technically would have to use something like integration by parts, or we can kind of be a little cheaty and look it up in the back of the book. If you look in the table of integrals in the back of the book, integral 82 says that v sine v turns into sine v minus v cosine v. And then, like I said here, this turned to a 1/4 sine squared v. And then the integral of cosine v is just sine v. Alright, now we get to plug stuff in. When we plug in pi, well, sine of pi is 0. We have a minus pi times cosine of pi, but cosine of pi is -1. Sine of pi is another 0. Sine of pi is another 0. Then we plug in 0. Well, sine of 0 is 0. Cosine of 0 is 1, but we're multiplying it by 0. Sine of 0 and sine of 0 are both 0. A lot of zeros. The only thing that actually survives is a negative pi times -1, or just pi. So the integral of this vector field through that surface, this helicoid that we have, is exactly just pi. We'll move on to problem 25. So this one is where we have a different vector field is xi plus yj plus z squared k. This time our surface is a sphere with radius 1 and center at the origin. So notice here that they didn't immediately give us an orientation to work with, but the sphere itself is a closed surface, so they want us to use the positive orientation, the one that points outwards. And we already noted in our last video that the positive orientation is given, at least when we're using spherical coordinates. So here, using spherical coordinates with our radius equal to 1, so rho equals 1, we have x equals sine phi cosine theta, y equals sine phi sine theta, z equals cosine phi. We found that we need to give it the positive orientation, the outward one, we need to take the r phi cross r theta and not the other way around. Phi has to come first for it to be positive. And the result of that, we got sine squared phi cosine theta I plus sine squared phi sine theta j plus sine phi cosine phi k. And so this is the vector that we're going to use to compute our surface integral. So the integral of f dot ds, of course, since we're going over the entire sphere, we let theta go from 0 to 2 pi, but we only let phi go from 0 to pi. And technically, it doesn't really matter which order we put this in, since our limits are just going to be numbers. We don't really care what order we do the integration in. It matters when we're taking this cross product, though. Of course, we take so x, y, and z squared. We have to remember what our components are, and we have to make sure that we plug in our formulas for in terms of phi and theta. So x is our first component. We get a sine phi cosine theta. We take the dot product, so we have to multiply that by sine squared phi cosine theta. Then we have y. Y is sine phi sine theta, being multiplied by our y component of our cross product. So we end up with a sine squared phi sine theta. I'm not going to fit the next one on this line, so let's move down here for the moment. Our third component is z squared. Z is cosine phi. So we have cosine phi squared, cosine squared phi if we want to, multiplied by sine phi cosine phi. And that's being integrated over phi and theta. So this looks maybe a little more complicated than it really is. Let's go ahead and actually kind of expand things out here. So we do have 3 copies of sine phi here. So we have sine cubed phi, but we have a cosine squared theta. We have, again, another sine cubed phi, and we have a sine squared theta. And then for this last one, we have a sine phi, but we have 3 cosines. We have d phi, d theta. And we can simplify this. So first of all, we have sine cubed phi for in both these terms. What's left is cosine squared and sine squared. Essentially, we can factor out the sine cubed, and the cosine squared plus sine squared turns into a 1. So we end up with a sine cubed phi plus sine phi cosine cubed phi, d phi d theta. One nice thing about this so far is that there are no thetas left in the integral. So the integral from 0 to 2 pi, I just can turn into a 2 pi on the outside. The rest of this, I'm going to have to figure out how I'm going to integrate sine cubed and cosine cubed and sine. Well, one thing that you can do here is you can take 2 of the sines from the sine cubed, and remember that sine squared is 1 minus cosine squared, which might seem like it's making things more complicated right at first, but it will actually help us overall. Because what I can do now is I can make the substitution of u equals cosine phi, which means that du is negative sine phi d phi. We have a sine phi here and a sine phi here. Those can both be factored out as part of our derivative. We do have to introduce a negative, but that's okay. So we have a negative, we have that 2 pi, we have the integral. Now remember what we have here, we have 1 minus cosine squared, but cosine is turning into a u, so we end up with a 1 minus u squared. And then we have plus just cosine cubed is a u cubed. So our integrand is very nice now. Our limits, we need to go ahead and plug 0 and pi into cosine. And you might remember from our last, from the actually the first video of this section, we had a couple of problems where we made this kind of substitution and we went from 1 to 1. That was because we were going from 0 to 2 pi. Here we're going from 0 to pi. That's not as bad, because cosine of 0 is 1, cosine of pi is negative 1. Which might seem like we're in the wrong order, but that's kind of why the negative's there. We can even take out the negative and switch the order if we want to. And now it's actually a pretty straightforward integral. We integrate 1 minus u squared plus u cubed. That becomes a u minus 1/3 u cubed plus 1/4 u to the 4th from negative 1 to 1. When we plug in 1, we end up with a 1 minus 1/3 plus 1/4. Then we plug in negative 1. So when we plug negative 1 in here and we subtract it, we end up with a minus negative 1, so a plus 1. Here we end up with a minus 1/3 that was times a negative 1 that's being subtracted. Overall, we end up with 3 negatives, so we have a minus 1/3. Finally, we are subtracting 1/4 times 1, because the 4th power gets rid of the negative, so we end up with subtracting a 1/4. That does mean that the 1/4s actually do cancel out. The rest of it doesn't. They actually combine. We get 2 minus 2/3. And overall, this comes out to be an 8/3. The inside turned out to be a 4/3 times the 2 pi that we already had. So 8 pi over 3 is the integral of this vector field through the sphere of radius 1. In essence, what it's saying is that the vector field, at least on average, is pointing outwards, because it's more following that outward facing orientation than it is going inwards. If this had turned out to be negative, that means more vectors are pointing into the sphere than are pointing out of the sphere. So at least we get an idea of what this actually means. For our last problem of this section, we're going to look at this surface integral where the actual vector field is yi plus z minus yj plus xk, and our surface is a tetrahedron. Let's go ahead and graph that tetrahedron. So it has the points 0, 0, 0, 1, 0, 0, 0, 1, 0, and 0, 0, 1. So kind of small, so we'll need to zoom in a little bit. Go ahead and connect those points by segments. And I'm going to make these segments a little thicker so we can see them better. There is our tetrahedron. Now, this tetrahedron has 4 sides to it. That means our surface integral is also going to have 4 parts to it. We're going to take this surface integral over each of the faces of this tetrahedron, and we're going to add them together to get the entire thing. Now, notice that since this is a closed surface, this does enclose the actual tetrahedron that's in the middle of it, then we need to use the positive orientation. That was our instructions say. And that means our normal vectors do need to point outward, which might feel a little weird for some of the faces as we go through them. I'm going to start with the the surface along the the xy plane. So that's the one that we see when we look just straight down. So essentially, we're just integrating over the triangle where the outer line here is y equals 1 minus x. Do note though, since we are trying to make a positive orientation, we need it to point outward. The unit normal is going to actually be facing downward. In fact, the unit normal here is going to be negative k. So, let's say for xy plane, which I'll go ahead and call S1, we can take our unit normal here to be negative k. Note that k could also be an orientation if we wanted it to, but since we don't want it to point inward, we need to pick that negative k. In fact, negative k is actually what we'd get if we use the orientation, or if we use the parameterization of x equals x, y equals y, and z equals 0. This is a nice parameterization of that surface, but in order to get negative k, we do have to take r sub y cross r sub x, which might not be the order that you expect it to be. R sub y, of course, when you differentiate x, y, 0 with respect to y, this goes to 0, that's still 0, that comes to 1. In other words, we get j that for r sub y. R sub k, for very similar reasons, is I. And j cross I is negative k. So essentially, we have a nice enough region here where our parameterization is very simple. It's exactly what we normally expect. We just have to pay attention to the particular direction that we're going through that surface. Our integral then, so the integral over S1 of f dot ds is going to be the integral from 0 to 1, 0 to 1 minus x. Remember, we are integrating over the triangle, and this is a limit for that triangle. So x is going from 0 to 1. So let's look at the picture here. So our x-axis is the red one. X is going from 0 to 1. Y is going from 0 down here to 1 minus x as that top line. And then we get to remember what our actual vector field is. We're taking this dotted with this vector. This vector is negative k. Our normal vector is negative k. So we have y, which is still just y, but our first component of our normal vector is 0. Plus, well, z is actually equal to 0 minus y, which is still y. But still, the j component of our normal vector is 0, so that didn't really matter either. Finally, we have x as our third component, dotted with our third component here is actually negative 1. So we're integrating this thing, dy dx. Of course, we're just really looking at the integral from 0 to 1, 0 to 1 minus x of negative x dy dx. No y's in here, so when we integrate that, it becomes a negative xy, evaluated from 0 to 1 minus x, really just turns into negative x times 1 minus x. Or in other words, we're really integrating, x squared minus x. The integral of x squared is a 1/3 x cubed. Integral of negative x is a negative 1/2 x squared. Still going from 0 to 1. When we plug in 1, we get a 1/3 minus 1/2. When we plug in 0, we get 0. 1/3 minus 1/2 gives us a negative 1/6 for this integral. Let's move on to, let's do the xz plane next. So here we're basically saying that y equals 0. But then x, we're just going to leave as x. Z is going to equal z. We're going to need to pick the correct parameterization again. So this time, we want to look at what's happening on the xz plane. X is red, z is blue. we're integrating over this triangle, but we do have to be pointing out this direction. That is negative y. Remember, the arrow here says that the positive y is this direction over here, but our normal vector has to point out to the negative. So our normal vector here is going to be negative j. And this actually turns out to be, what, rz crossed with rx? Or, no, actually it's the other way around. I guess it's rx crossed with rz. Because rx is I, rz is k, if you're following this parameterization, just taking those derivatives. And then I cross k is negative j. But we don't really have to worry too much about that. Once we know what the orientation actually is, then we can actually go ahead and use it. So the integral over s, I guess we're calling this s2 of f dot ds. I'm going to find limits for this where I do I'm going to do dx dz, because it'll turn out to actually be the easy way of doing this. So dx dz. Notice here that z is going from 0 to 1. And then when we actually look at this triangle, so again, looking at it like this, we're integrating over this triangle. Z is going from 0 to 1. The x is going from 0 here out to the line x equals 1 minus z. And then our integrand here, actually, I guess I need space to actually write it out. It'll simplify similar to the last one, but I do want to write the whole thing. Remember here, the first thing we put in here is f. F of our first component of f is y, but y is equal to 0, so we have a 0 there, times the first component of our normal vector, which is 0, because the I is 0 here. We have the first component of our vector field at this point, so z is equal to 0, but y is equal to 0. So we have z minus 0 times the second component of our normal vector, which is negative 1. Then we move on to our third component of f is x. But that's times the third component of our normal vector, which is 0. And I said this was dx dz. Of course, everything, like I said, simplifies quite nicely. This is 0, that's 0. This is just z times negative 1, so minus z, dx dz. And now the reason why I wanted to put it in that order is if you compare the format of this particular integral that we have here to this integral that we have here. Now we have different names for things. Here we have y dx, whereas here we have dx dz. But then there's no other y's in here, and all the x's, we have a 1 minus x and a negative x. Here, there's no other x's, and then the z's are a 1 minus z and a negative z. So just by changing the letters, swapping out the letters, so x for z and y for x, we get the exact same thing. And so when we do the integration, it's not going to change the answer. We're going to get the same result of negative 1/6. All right, moving on to the what's left. We have the YZ plane, which I'm going to call S3. Of course, here, this is where x equals 0, but we're going to leave y equals y and z equals z. If we actually go ahead and look at that, remember we are... Actually, I probably want to look at it in this way. So we have the positive direction going that way, positive direction going there. We're looking at this triangle again. Again, we're going to do the same kind of limits using the fact that this line here is y plus z equals 1. Again, the actual normal vector has to point outward, so it's going to point this direction, which is negative I, because the positive x is this direction. So here, n is equal to negative I. And if we actually look at the r cross r sub something cross r sub something, so which order do we want this to be in? If we do r sub y cross r sub z, well, r sub y is going to be 0, 1, 0, so that's going to be j. R sub z is going to be 0, 0, 1, so that's going to be k. But j cross k is actually positive I. We actually want it the other way around. So we need r sub z cross r sub y. But again, that really, the order that we put our variables in won't actually really play too much of a role. It's just a matter of making sure that our parameterization here does work nicely with the orientation that we've chosen. So the integral over S3 of f dot ds. We're going to have a double integral. This time I'm going to pick the ordering of dz dy. So I'm going to have from 0 to 1 for y. I'm going to have from 0 to 1 minus y for z. You might notice you might figure out why I'm actually doing that. It'll be very similar to what we did for the last one. But we need to go ahead and plug in our values. So remember here, y is y, z is z, but x is 0. So we'll go ahead and leave them in that form for the first two components of f. We have a y here, we'll have a z minus y here, and then we'll have a 0 for our x component. Or for our z component is x, but x equals 0. We take our normal vector here, that gives us a negative 1 here, a 0 here, and a 0 here. We add those together. Of course, everything is 0 for this last part, but we have a negative y here. And just like on the last two, we have the same kind of form. So here, instead of having the z here, z here, z here, we have a y in those three places, and now the x is turned to a z. But the format is exactly the same, and so when we do the entire integration, we'll get negative 1/6 again. So just kind of saving some work. It's not that the work is really complicated, but we might as well save any time that we can. Finally, we have the side that's not a coordinate plane, which I'm going to call S4. This plane, if you want to give it an equation, would be the plane x plus y plus z is equal to 1. That would be the plane that passes through all 3 points of 1, 0, 0, 0, 1, 0, 0, 0, 1. If you add those coordinates up, x plus y plus z, you always get 1. We can actually view this as the graph of a function. We can actually just solve for z. So z equals 1 minus x minus y. And if we think about the upward orientation, so when we look at the graphs of functions, the orientation that we were looking at in our formula back on the first page of this was the upward orientation, and that actually agrees with the positive orientation that we want. So we want the orientation that's pointing out this direction, and that's the one that's going mostly upwards. It has a positive z component to it. So we'll go ahead and use this formula here. So here, remember the P and the Q and R, those come from f. Those are the components of f. And we'll take the derivative of the function with respect to x and y, and we'll multiply them by the components of f. But remember, we do have a minus sign for the first two terms. So dz dx, of course, is just -1. dz dy is also -1. So that means our surface integral over S4 of f dot ds, we are integrating over that same triangle that we've been doing before. So we're still go from 0 to 1. I'm going to let y go from 0 to 1. I'm going to let x go from 1 minus, from 0 to 1 minus x. Am I done that in the wrong order? Okay, yeah, okay. I wanted to do dx dy. So I'll have dx dy at the back here. So y is going to go from 0 to 1. X is going to go from 0 to 1 minus y. Because the boundary line of that triangle is x plus y equals 1. I can solve for either x or y just fine. But I need to have negative p. P is my first component of f. Go back 2 pages. That's a y. So I have a negative y times my derivative of z with respect to x. So I'll be times -1. Minus q. Q is my second component of f, which is z minus y. Though keep in mind z is actually 1 minus y minus x. Sorry, 1 minus x minus y, and I'm subtracting y from that and multiplying by -1. And I'll need actually a little bit more room. And then I add in r. R is my third component of f, which is just x. And I don't have to multiply that by anything. All right, simplifying this thing. We have a positive y. We'll end up with a... So to remember all of our signs here, so this negative here doesn't change those signs because we're multiplying by a -1. So we actually have a positive y plus 1 minus x minus y, and plus x. Ultimately, what happens here is this positive y cancels out one of the minus y's that we have in here. This plus x cancels out the minus x that we have in here. So we'll end up with a 1 minus y overall. When we integrate this, because I chose dx dy, there's no x's in here, so we can kind of breeze past the first integral. So we end up just multiplying this by the 1 minus y that's in there, which actually just turns that into a square. We could expand this out and do the integration from 0 to 1 that way, or we can just keep in mind that by a simple substitution of something like u equals 1 minus y, we can just treat this as u squared and get a 1/3 u cubed, or really just a 1/3 1 minus y cubed. The only thing to pay attention to there is that when we differentiate this, we do get a negative. So we end up having to put a minus sign there. And we evaluate that from 0 to 1. Plugging in 1 gives us 0. Plugging in 0 actually gives us a 1/3 times 1, so a -1/3 that's being subtracted because this is the bottom limit. Ultimately, we get a 1/3. And therefore, the total integral, the integral over the entire tetrahedron of f dot ds, is going to be the sum of these. Remember, we had, for the first three, all turned into a -1/6, and this one turned into a 1/3. When we add all those together, well, actually, the 1/3 will cancel out to -1/6, but we'll still have a -1/6 left over. So that's the total integral, the total surface integral over that entire tetrahedron. Now, this very last result is something that we will find a lot easier to calculate when we get to the divergence theorem, because we're actually integrating over the surface of a closed surface that's bounding a particular volume. And maybe I'll remember to bring up this example again when we're going through examples for section 16.9. But for now, that's just going to be kind of a teaser. This is probably the harder way of going about and solving this problem. Even though the problem is really just finding the surface integral, doing it directly may not be the easiest way of doing it. But hopefully by this point you've got an idea of how to take surface integrals both of a scalar function and of a vector field. And in the next two sections, we'll go through some theorems that might make these easier. So meet me in those, and we'll see where it takes us.